Hello and welcome back. In this video, we'll have a short introduction of how we can program graph neural networks in PyTorch. Graph neural networks have emerged recently as a very exciting alternative to other ways of creating neural networks. The graph neural networks are centered, as the name gives it away, on graphs. These are connections of node and edge that are connected by edges. And in particular, we can use the graph to describe the properties of, say, a social graph, or natural sciences or engineering, for example, a molecule or crystal. So graph neural networks, in this sense, represent a shift in paradigm. We move away from machine learning, where we define lots of feature variables, often in material science also called descriptors, and use the structure of the material itself to create predictions and learn the relationship of how the substance we want to analyze is structured and how this is connected to the macroscopic properties of it. Here in this exercise, we focus on the QM9 dataset, which is a molecular dataset and publicly available, and we can use it for a very small graph neural network to illustrate the main points. The main code for this exercise were taken by this nice book, Machine Learning in PyTorch and Scikit-learn. If you run it on free GPUs on Colab, you also need to install the relevant packages. Here's the magic line for it. And here we want to now go over how we can define a graph neural network. We import Torch, and in particular now the extensions to it that are related to graph neural networks. The dataset that has a specialized data loader that sort of replaces the standard data loader from PyTorch, and now the specific functions that are related to graph neural networks, in particular the graph neural network, the convolutional part, and the pooling. The library network X is used to visualize graphs, and so we import this as NX. And this complements our typical visualization libraries. And as usual, we need the standard functionalities from PyTorch, such as the neural network module and the functional. First of all, we need to access the data. As we said, we want to use the QM9 dataset as part of the PyTorch geometric, and that provides us with a convenient wrapper to access this data. So we can just use it as we've imported the respective functionality before. That will, if we don't have it, download the data and add it to our local file structure. As always, let's start with a little data exploration and exploratory data analysis. And the base format of the library PyTorch geometric is the data object that describes the graph. So this is like an extension of the data we have encountered in, for example, standard convolution neural networks and images. We really need now an object that's handling the relationship between nodes and the connection between nodes, the edges. So the part DataX describes the node features. For example, we could think of these nodes as the atoms. Right? So we have the number of nodes and the node features. So we need now more variables to describe what we have. For example, we could say if a node is an atom, we could have the mass of this atom, the kind, or the electronegativity, or other variables or features that describe the specific properties of this atom. The target or the label is always given by Y, and here we have it in data Y. In graph now we can have multiple layers of targets. We can have targets that affect the whole graph, for example, as we will do in our case here, the isotropic polarizability, but we can also have other parts that, for example, want to do graph predictions on nodes or edges or something like this, so we need to have more flexibility like this. Because the graph is made of nodes and edges, and the edges connect the nodes, we also need to have a way to describe which edges connect which nodes, and we use the data edge index for this in this special format. And these describe which node, in our case, for example, an atom, is connected with which other node. And the shape of this matrix is this one. We always have two, because one node is connected by two nodes are connected by one edge. And in a similar to the case that we have node attributes, for example, describing our atoms, we have now edge attributes. For example, that could be the way the chemical bond is characterized between those two atoms that this edge connects. The data object is also quite flexible and allows us to store new variables in this object depending on what we need. So let's look at the first element. So our graph is here the first molecule in this data set, and we can just print some properties like the number of nodes. These are the atoms, at the edges these are the bonds, the features of the atoms and the bonds, and so on. And you can see that we have 5 atoms in this molecule, and these are connected by 8 bonds with these number of features. The node and edge features are then represented as matrices, or rather in tensor format for PyTorch. And we can, for example, visualize this molecule using the Network X package. And if we do this, we can see how these nodes and edges belong together. Now let's move to the graph neural network setup. So we need to define a graph neural network, and it's overall fairly similar to how we would define a neural network in standard PyTorch as well, except of course now that we need to make sure that we make use of the extended capabilities that the graph brings us. In particular, that means that we use the NNCon from the PyTorch geometric library instead of the normal standard convolution network layer. And this one implements the approach taken in this paper. And we also need to have the global app tool for the node features. For simplicity, we predict here now a single number that affects the whole graph, in our case, the polarizability. And we also need to exploit the edge features. Here we use 2 small fully connected networks. And since we don't use much flexibility, we use an alternative way of implementing this, the sequential method. Normally, we've seen so far that we use a class in PyTorch to program our more complex neural networks, but because we only want to have a very small one, we can use this convenience format here. So in a more compact way of writing, our network will consist of the following. We have 2 graph convolution enabled. They will pass through an activation function, and then we have the fully connected layers that takes the output of the graph convolution and then one fully connected layer to make the regression head, as it's called. Finally, we want to predict a single number. So our overall network is still defined as a class because it's fairly complex. We inherit, as always, from the network module and initialize it and initialize the base class. And here we have our small neural networks. For the edge features, we could also have it as a class definition, but we can make use of this NN sequential functionality because it's only 2 layers with an activation function. This defines this model as well, and this saves us the trouble of defining a forward pass and so on. Now we set up the graph convolution layers. We use the NNConv module with the number of node features, and we use the edge networks. So these are the parameters that are used in the graph convolution layer to make use of the edge features. And then we have a dense fully connected layer for the regression and a linear output for the number we want to predict. As always, we need to define the forward part. One of the things we need to do is to unpack all the data. So we take the data objects and sort of retrieve all the information that's in there. We could do this in several lines, but we can also write it more compact in this way. Now we build our network. So we pass the graph convolutional layer with the edge information through the activation function. Again, we could do this in several steps, but we can chain this operation here, add the node features with the global add pool, and have the regression head to predict our final number. As always, we need to split our data into training and test sample, and PyTorch here also provides similar functionality to the scikit-learn interface using PyTorch due to its data random split. So we have the whole data that is available to us, and we give it here with the indices so that we have roughly these proportions between the test, training, and validation set. And then the final network training is then very similar to what we would expect from a standard PyTorch network. We create an instance of our network, create the optimizer, give it the parameters that it needs to be optimized, use the LM optimizer with a fixed learning rate. Of course, you could also use a learning rate scheduler later. Take the training epochs. Because the data array has now so many possible target variables, we need to choose one, in our case the probability, which has the index 1 in the data set. As always, we also need to make sure that we run the appropriate device, like a GPU if we have one, and move the network through the device. And then we define the training loop, and here we follow the standard PyTorch patterns. We move the network into train mode, iterate in batches over the train data, move the data to the device, erase any previous gradients, apply them to get the output, get the loss function. Here we have an implicit definition where we use the mean squared error because we do a regression task. Right, here's some magic to convert the numbers such that we can compare the output predicted by the network with the target representation in our arrays, and do the backward propagation optimization to get the new weights. So this is really quite straightforward when we have used PyTorch before. The complexity of using graph neural network is sort of previously in the definition of our network itself. In the evaluation, we also then get the test data. We move the network to evaluation mode, get the empty arrays for the predictions and the true values, move the data and get the predictions. And again, we need to get the output into NumPy format, as we've seen in other cases previously. So we need to move it to NumPy format to the CPU and detach it from the computation that PyTorch does itself, and then add all of this together so that we finally get a scatter plot. And as you can see for this somewhat simple example, we get a more or less perfect straight line. And the key was in this graph neural network approach that we don't create specific features that describe our molecule, but we've described the properties of the atoms and their connections.